Hi, and welcome back to my series of videos for General Chemistry 1. By now, you've probably had another test in your General Chemistry class. I hope you did well. And that means you're just about halfway through with the course. You're quickly becoming more skillful and a knowledgeable chemist, and you can now do plenty of things that would have seemed much harder for you when you first started the class. Today, we'll start talking about light, and how light can interact with atoms. I think it's one of the most interesting parts of this course, and I hope you will too. By the end of today's video, you'll know how we can tell the age and temperature of a star. And to get there, we'll start with one of the oldest questions in physics. Is light a particle, or is it a wave? This is a question that's bothered some of the greatest minds in all of science. Isaac Newton struggled with it, and eventually became convinced that light is made up of particles, which he called corpuscles. But about the same time, the astronomer Christian Huygens, who discovered the rings of Saturn, determined that light is a wave. Over 200 years later, some of the work of Einstein suggested that light is made up of particles again. He called them photons. In fact, that work was the primary research that led to Einstein receiving the Nobel Prize. It wasn't his theory of relativity, which came later. So, there was evidence supporting both sides, that light is a particle and that it's a wave. In the next two videos, we'll talk about how all these experiments are resolved, but for today, we'll just talk about one of the most famous experiments that tried to solve this problem. That was done in 1803 by Thomas Young, exactly 102 years before Einstein showed that light can act like a particle. Young also has the honor of being the only scientist I've talked about so far in these videos who doesn't have a mustache or a beard, but he was a pretty bright guy anyway. Young's proof that light's a wave is amazingly simple. All you need to do is take a light source, let the light shine on a card that has two really narrow slits cut into it. Then you look at the pattern of light that comes out the other side of the card. What kind of pattern should we see? Well, if light's made of particles, Einstein called them photons, then we might expect them to act like bullets, meaning they'd travel in a straight line. The ones that hit the card would bounce off or maybe get absorbed by the card, but the ones that happen to go through a slit would make it to the other side. If we look at where the photons go, we'd expect to see two spots, one for each of the slits that the photons pass through. On the other hand, if light's a wave instead of a particle, we'll see something much different. Imagine that the waves act like water waves. In that case, they'd hit the card and be able to get through only where the slits are. So on the other side of the card, you'd end up with two waves, one coming from each of the two slits. Now pretty soon, those two waves would meet each other on the other side. When they do, something interesting happens. Again, imagine water waves. If two water waves happen to meet, then the waves would combine. The tops of the waves would add together to become even higher than they were before. The same thing would happen with light waves. The half circles that you see here are the tops of the light waves. Wherever the tops meet, they add together and become higher. For a light wave, a higher wave means brighter light. So, if we put a card down here, what we'd see is bright spots where the tops of the waves meet and darker spots in between. That's what's called an interference pattern. So we have a way to decide whether light's a particle or a wave. If it's a particle, when we do the experiment, we'll see two bright spots on the far side of the slits. But if it's a wave, we'll see a pattern of a lot of bright and dark spots. So let's do that experiment. What I have here is a laser. It makes a nice bright green dot. And I've set it up so that it shines on a white plate. Now, in front of the laser, I'll put a card that has two tiny slits very close together. And what you see is that we do get a pattern of bright and dark stripes. That tells us that light is a wave. If it were acting like a particle, I'd just see two dots, one for each of the slits. So, this experiment seemed to solve that issue. Light is a wave. In the next video, we'll see that this wasn't the last word on the question of whether light's a particle or a wave, but for now, we'll talk about light as though it is simply a wave. So, let's talk about waves in general for a minute. Waves have four properties that we'll care about. First, there's the height of the wave, which we'll call its amplitude. Next is its wavelength, which is the distance between the peak of one wave and the peak of the next, and it has this symbol, which is the Greek letter lambda. When you look at a spectrum like this one, it usually gives you some information about the wavelength of the light you're looking at. In this spectrum, the wavelength is lower on the left, meaning that the waves are shorter, and they increase as you go right. As you can see, gamma rays and X-rays have the shortest wavelengths, and radio waves have the longest. In the middle are ultraviolet, visible light, and infrared. Notice that the wavelength is often measured in meters. For example, radio waves can have wavelengths from 0.1 meters all the way up to thousands of meters. If you look at the visible light region, you can see that it ranges from about 4 times 10 to the minus 7 meters to about 8 times 10 to the minus 7. When we talk about visible light, it's often convenient to use a different unit than meters so that we don't have to use scientific notation. For that reason, we often measure wavelength in nanometers. 1 meter contains 1 billion nanometers, so 1 meter equals 1 times 10 to the 9th nanometers. Let's stop for a minute and practice converting those. For example, emeralds have a beautiful green color corresponding to 601 nanometers. We can use our conversion factor to change this to meters. We want the nanometers to cancel out, so it goes in the denominator and the 1 meter goes on top. That gives us a result of 6.01 times 10 to the minus 7 meters. The next property of waves we want to talk about is the frequency, which has this symbol, the Greek letter nu. It looks a bit like a letter V. Remember, light waves are in motion, and the frequency tells us how many waves go by in 1 second. For that reason, the units for frequency are seconds to the minus 1 power. Another way to think of this unit is 1 over seconds. This seems like a really weird unit at first, but it makes more sense if you think of the unit as meaning per second. So, for example, if the frequency is 5,000 seconds to the minus 1, it means that there are 5,000 waves that pass by per second. If you think about it that way, you can see that if the waves are short, more of them will pass by every second than if the waves are longer. So a wave with a short wavelength will have a high frequency, and vice versa. We can calculate these using this simple equation. C equals lambda times nu. So the wavelength times the frequency equals c, which is the speed of light. This is a number you should learn and remember because we'll use it often in this class. C, the speed of light, is 3.00 times 10 to the 8th meters per second. Remember, when you use this equation, you'll want the units to work out correctly, so you'll want the wavelength to be in meters and not nanometers. So, for example, radio stations usually identify themselves using the frequency of the radio wave they use. One radio station where I live is 89.5 FM, which means its frequency is 89.5 million seconds to the minus 1. So 8.95 times 10 to the 7th seconds to the minus 1. Suppose I want to know the wavelength of this signal. We'll use this equation. We plug in the speed of light and the frequency and solve for the wavelength. What we get is 3.35 meters. That's a pretty long wavelength for light, much longer than visible light, which we saw could be measured in nanometers. But if we look at the spectrum, we can see that 3.35 meters is pretty normal for a radio wave. The last property of waves we want to talk about are their energy. It turns out that waves with short wavelengths and high frequencies have a high energy, and waves with a long wavelength and low frequency have a low energy. So, for instance, gamma rays and X-rays have a very high energy, and radio waves have a very low energy. This makes sense when you remember that gamma rays and X-rays have the ability to break the chemical bonds in DNA, which can do a lot of damage, but radio waves are very safe. It turns out that the energy of a wave is related to its frequency by this equation. the energy is equal to h, called Planck's constant, times the frequency. Planck's constant is another one that you should learn as soon as you can, because we'll use it a lot in this chapter. It's a very small number, 6.626 times 10 to the minus 34 joules times seconds. So, for example, the radio wave we were just talking about had a frequency of 8.95 times 10 to the 7th seconds to the minus 1. That gives us an energy of 5.93 times 10 to the minus 26 joules. That's a really tiny energy. And that brings us to some of the research people first did with this new information. A lot of it relates to astronomy because people like stars. And if you like looking at stars, one of the things you notice is that stars don't all look the same. They can have really different colors, for example. A really easy example, if you live in the northern hemisphere, is Betelgeuse, which is a red supergiant. It's so big and so close, relatively speaking, we've even taken some decent photos of it. Well, decent for something that's 640 light years away. Betelgeuse is the left shoulder of Orion, and you can tell it's reddish-orange even with your naked eyes. Meanwhile, the right foot of Orion is Rigel, and that one's a blue star. For a long time, people thought that the color of a star might tell you something about its temperature, just like a hot piece of metal goes from glowing red to yellow as it heats up. So a yellow star would be hotter than a red one, and a blue star would be even hotter than that. And the reason you care about that is that the temperature of a star can tell you about how old the star is, and sometimes how large it is. So, for instance, the stars near the center of this galaxy are bluer, which means they're hotter and probably younger than the stars out here, which are redder. Toward the end of the 1800s, telescopes had gotten good enough to allow us to measure the colors of individual stars pretty accurately. Astronomers were pretty happy about this, because it meant that we could learn a lot more about how stars form and how they age. So the first thing to do was to figure out the exact connection between a star's color and its temperature. Different colors of light have different energies, so as something gets hotter, it gives off light with a higher energy. If something's really hot, like a star, it might glow red, like Betelgeuse. And if it's even hotter, it'll glow blue, like Rigel. Even your body, obeys this rule. Your body's warm, so you give off light. But since you're not as warm as a star, the light that you give off has way less energy, and it's down here in the infrared part of the spectrum. That light you're giving off is what people see when they look at you using infrared glasses. There's an equation relating the temperature of an object to the frequencies of light it gives off. It's called the Planck equation, and it imagines stars to be like idealized objects called black bodies. We won't worry about that equation in this class, but it's something we'll talk about a lot in the physical chemistry course, which I hope you'll take someday. Here's what you get. This graph has frequency down here, and the height is energy. This is for a black body at 98.6 degrees Fahrenheit, so basically, this is the spectrum of light that your body's giving off right now. Planck's equation shows that your body gives out a pretty small amount of light at really low frequencies out here, then it maxes out here at around 20 terahertz, and then it drops off again. The important thing here is that this entire graph only spans the infrared region. Lower frequencies like microwaves are crammed all the way down here at the edge, and higher frequencies like visible light are way off the scale. They're all the way to the right past the edge of the graph. The Planck equation works really well for stars too, which was the whole point to begin with. If you plot out the spectrum of the sun, for example, you find out that it matches up with the plot you get from the Planck equation at 9940 degrees Fahrenheit. You can see that the curve's pretty high in the red and yellow regions as well as in the infrared, and that's just the way our sun is. Meanwhile, Rigel's spectrum matches up with a plot of the Planck equation at a temperature of 19,300 degrees Fahrenheit. It's way hotter than the sun, as you might expect. And the curve shows that Rigel is blue-colored. You'll also notice that Rigel's curve is way higher than the sun's. That's because Rigel's much brighter, as you might expect, because it's also hotter. Planck's equation predicts that too. In fact, this graph actually shows three plots. It shows the one for Rigel, it shows the one for the sun, and it shows one for the human body, which I showed you earlier. It's way down here in blue. It looks like a flat line here because the peak is so much smaller than the one for the sun. That makes sense since you're not as hot as the sun is, and you don't glow as brightly as the sun does. Well, that's enough new material for today. When we talk again, we'll look at light a bit more, especially the reasons elements have the colors they have. So until next time, have a good week.